Okay, so for this video, we're focusing on page 4, and now we're looking at the difference between net and total area. So we know from previous videos that net area is basically an area that's obtained from a definite integral. So just you put a function in, and it gives you the area captured between the function and the x-axis, or the function and the y-axis, depending on your perspective. And from there, you could have some positive areas, you could have some negative areas. And then when you take the sum total of those areas, you have a little bit of ebb, you have a little bit of flow, and then you put it all together and you have a net quantity. But if you look at some of the examples on this page, especially towards the bottom, you see that we're looking at just areas, shaded regions. It's calling for positive values, right? So even areas below the x-axis, we would want to represent that as a positive area. So like if you think about the area of a circle that's centered around the origin with a radius of whatever, it doesn't matter. Part of it, or half of it, will be below the x-axis, half of it will be above the x-axis. If you were to find the area of each of those parts using definite integrals, the bottom half and the top half, you'd get a positive area and you'd get a negative area. And when you added those two together, you would get 0, and you'd say, well, the area of a circle is 0. In all cases, that's wonderful, right? So math is broken, and that's the obvious conclusion from this. The reality is, it's not broken, it's just we have to look at it in a different way. In that context, we're looking for the area of a geometric figure, right? It just so happens that that geometric figure is centered around the origin, right? I could center that same geometric figure 10 units above the x-axis and have the entire circle in the top two quadrants 1 and quadrant 2, right? In which case all of the area would be positive, right? So it's just a matter of choice that I'm putting it on the x-axis, but it could be anywhere, right? And that's the same for these figures. Now and looking at number 5, for example, you can see part of it is below the x-axis. But if I were to translate this function upward, I could have the entire region in the positive portions of the graph. All right, so when we're looking for total area, we're looking for just what the area would be, assuming that each area is a positive value. All right, so looking at number 1, find the net and total area. All right, so the first thing I'm going to do is I'm going to draw a quick sketch. Now, you could use your calculator for this, but it's kind of, I'm going to say it's a little dangerous to always rely on your calculator, but that's, honestly, I don't think I'm telling you anything you haven't heard already. I'm going to say it can be misleading to use your calculator. All right. Just like it's misleading for me to use this pen right now because for whatever reason it's not working. Stylus and palm rejection. Disconnect because it thinks it's an Apple Pencil. All right, that's why. I'm going to use... well, at least it's writing something now. All right, yeah, small victories. Now, I try not to cheat, because how many times have I done this problem in my career? Like a bazillion. No, like probably 10. And so I know what the function is supposed to look like, but I will talk you through how one would get it, a quick sketch of the graph without having known or having, advanced knowledge of it. See, I have a common factor of x. I can pull that out. X squared minus 4. Factors of x squared minus 4. Conjure up your inner algebra 1 self. Actually, maybe not. Don't do that. Because maybe your inner algebra 1 self didn't know how to do this. But now, you've been doing it for years, so now you know how to do it totally. All right, so the roots... Are we going to have to do this by hand? Are you really ever going to have to do anything by hand? Like, really? 0 plus or minus 2. 0, here's a negative 2, and here's a positive 2. Honestly, I could say without exaggeration, I was able to probably do 99% of all the stuff that I was asked to do as a student without having to do it by hand. So it is what it is. So anyway, we have x-intercepts at negative 2 and 2. This is a cubic function, which generally looks like this. That's the positive cubic function, which is the one that we're concerned with now. We're only concerned with this function on the interval of negative 2 to 2. So I'm going to go with dashed curves because I don't care about that part of it. And then I'm going to go meh, meh, an additional meh, and then I'm going to follow it beyond. You know, it's going to have a little arrow there, a little arrow there. Now, the way I drew it, it looks like it would be symmetrical. You may remember from pre-calc the idea of an odd function. And that's what this one is. There was a little test that you could use in order to determine whether or not a function was odd. You replace all your x values with negative x and see if you end up with the exact opposite of the original function. The better way of doing it, or at least a more sight recognition based approach, would be to just take note of all the powers on the right hand side. If all those powers are odd, then it's an odd function. If all of them are even, it's an even function. And if it's some kind of mixture, it's neither. All right, odd functions are symmetric through the origin. I might have mentioned this already, but this is one of those topics, the odd even function. Before I taught calculus, I had taught just pre-calc, and I would gloss over this topic being like, I'm sure it's important to somebody, but it's not important to us, so we're just going to give it like 5 minutes and then move on. It's so important when it comes to integral calculus, but you don't necessarily know that until you get there. And a lot of things related to math are like that. So net area. Very simple. Take the function, put it in a definite integral, x cubed minus 4x dx, on the relevant interval, in this case negative 2 to 2. And we'll get an answer. You could spit out, you have the calculator spit out the answer, that's fine. The total area. There are, off the top of my head, probably 2 or 3 different ways you could do it. But here we're only really concerned with setting up the integral because, again, you just pop it in your calculator to get the result. All right? We know that this is going to be a positive area right here. This is going to be a positive area, and this is going to be a negative area. The net area is going to be equal to 0. You put that in your calculator, it will be equal to 0 because it is symmetric. All right. One thing that I could do is double the positive area. So if I want to find the total area, Alexa, stop. Sorry, I had an alarm. I could double the positive area. So one thing that I can do would be to go from negative 2 to 0 of that function x cubed minus 4x dx. Take that result and double it. Or, and this is a little bit of a more universal approach. This goes also back to years past. Algebra 2 is where this one should have been first introduced, would be the absolute value of a function. The absolute value of a function takes the function itself and makes any part of it that's positive, or actually keeps any part of it that's positive, positive, but then takes any part of it that's negative and makes it positive. All right, so I got a little shaky diagram there, but what it'll do is take only that negative component and it'll take that negative component and make it positive. So another way that you can handle it would be to go from -2 to 2. So -2 to 2. We still have that x cubed minus 4x dx. Like I said, -2 to 2, but take the absolute value of the function. Now, most people look at this and say, that actually sounds wonderful, because I now have a pretty easy recipe for coming up with net area and total area. The net area, and we'll just look at number 2, if I just need the numerical, the computational, the however you want to say it, net area, and for number 2, I'm gonna, for a sine function, part of it is going to be above the axis, part of it's going to be below the x-axis. Poor quality integration symbol. 0 to 3 pi over 2. I'll have sine x dx. That'll give me some answer. Not overly concerned again with what that answer is, because we could put it in the calculator. Although we actually did play around with this problem for a little bit on a couple, I think it was page 2. We know that each arch under a sine function has a total area of 2. So to get to 3 pi over 2, it's actually going to give you a result of 1. I mean, fun fact of the day if you want. Total area. But again, something that you could get right from your calculator, so I'm not overly concerned with that. Total area, this is where I get sneaky. Look at me. Look at this guy. Copy. Paste. And again, I'll just do a quick sine function just so you have it. So you don't have to refer back to the previous video. We know that this is 2. And we're only going from here to here. So we're going to have 2 and then a -1 here. So 2 minus 1 is 1. But if that negative becomes positive, that -1 becomes a positive 1. 2 plus 1 would be equal to 3. All right. Again, like I said, I'm kind of glossing over the solution to the integral because you can just pop it in your calculator and get the answer. Shortcut for absolute value, alpha window. First option there will bring up, I mean, there's other ways to get it, but that's probably the cleanest way to do it. I'm actually going to make another video for the rest of the problems on this page. I figure that